So the next talk will be presented by Robert Pavel. He holds a prestigious Metropolis postdoc fellowship at Los Alamos, and this paper is co-authored with Christoph and a couple of other co-authors that will be mentioned in the talk, and so I will let you speak there. Thank you.
All right, can everybody hear me?
No.
Okay. So I'm checking.
Yeah, you should be on.
Cool, test. Yeah. All right. Hi, I'm Robert Pavel. I'm from Los Alamos National Lab. Myself, Christoph Junhans, Sue Mizewski, and Tim Gurman use Charm++ to support multi-scale, multi-physics on the Trinity supercomputer. This was done as part of the Exascale Co-Design Center for Materials in Extreme Environments, ExMatEx. It was one of 3 DOE Office of Science Application Co-Design Centers from 2011 to 2016. It was a large-scale collaboration between national labs, academia, and vendors, and we collaborated with related DOE and NSA co-design efforts. Our goal was to establish a relationship between algorithms, software stack, and architectures needed to enable exascale-ready applications, with the ultimate objectives of identifying the requirements for the exascale ecosystem that are necessary to perform computational material science simulations, which is hopefully going to be useful for the previous talk, and demonstrate and deliver a prototype scale-bridging materials science application based upon adaptive physics refinement. That application being the Tabasco. Our test problem was modeling a Taylor cylinder impact test. I'm not going to go into the science too much because I don't know it, and this is a Charm workshop. But the simple Taylor model cannot account for the twinning and anisotropy of a tantalum sample used in nano experiments, and the final shapes do not match. So if we used a more accurate simulation, we could match the shape and do science. All right, our basic workflow was we have a coarse scale model. We break that up into subdomains. We then do adaptive sampling with the assistance of a database. And when needed, we perform fine scale models. Basically, the fine scale models are expensive. We don't want to do those if we don't have to. And adaptive sampling lets us avoid doing those. The code itself, Tabasco, was the task grid-based scale bridging code. It demonstrated the feasibility of at-scale heterogeneous computation composed of a coarse-scale Lagrangian hydrodynamics code, LULESH, dynamically launched constitutive model calculations, and we used results of fine-scale evaluations stored for reuse in databases to do Kriegan and other interpolation schemes. And yes. Okay, and we also combined this with an asynchronous task-based runtime environment with persistent database storage. A framework consisting of the set asynchronous task-based runtime. We used Charm++, which built and ran on Trinity, so everyone here should be happy. We also used a few other options, which I won't go into too much because it's not Charm. We used different nearest neighbor search algorithms. M-tree and Flan both worked perfectly fine. And we also used database storage techniques. We had an in-memory hash map that was a fallback, which obviously does not work for very long runs. A POSIX database where we basically just wrote a bunch of files and broke the file system repeatedly. That did work quite well for us, but not so much for anyone else. A data warp-based one, which also worked quite well. And a Redis database, which we never actually used on Trinity for many reasons, but it works great on everything else. In terms of Charm mapping, we mapped the coarse scale model, which is our LULESH class, to to multiple chairs. If this were an MPI code, they'd be ranks, but we did not use node groups, so oversubscription is good. We mapped the fine scale models to chars as well in 2D arrays. That we had one of those per element. We also had an evaluate char, which corresponded to our fine scale calls as needed. Again, we'd have those on the order of 1 per element. We also had nearest neighbor search char, which we treated more as a service, so we'd fine-tune the number of those we had in relation to the elements and domains. And we had database interface, which again, we treat as a service. All of this ran on the Trinity supercomputer, which is a very pretty computer, as you can see right there. It consists of a mixture of Intel Haswell nodes and Intel Knights Landing processors. And our charm breakdown was pretty simple. On the Haswell nodes, we put the coarse scale chairs, which are the Lulesh's nodes. Also on the Haswells, we put the neighbor searches. And also on the Haswells, we put the neighbor interpolations, so the adaptive sampling ones. And then depending upon what phase of Trinity we were in, we put the fine scale and evaluate chars on either KNLs or Haswells. And we also used the burst buffer nodes to store our database because they were much faster. We have some initial results from phase 1, in which we showed weak scaling and strong scaling. We have a range of data. This was just a single sample we selected. With our brute force approach and adaptive sampling, weak scaling, we got out to on the order of 128 nodes of no problems. And 256, we had to fine tune our problem a lot more. And on strong scaling runs, everything worked pretty well, not amazingly well, but pretty well. And just in terms of science, because people like pictures, this is the tantalum sample. As you can see, over time, it deforms. So that is basically close to what we wanted, which is good for science. Also, I just want to say thanks to UIUC for helping us to debug this. We wrote most of it ourselves, but when it came to debugging this with Trinity, contacting you guys was very useful. And the more important, more interesting part, that I'd say at least, were the early work on the hybrid runs. As mentioned, Trinity is a machine of 2 stages and 2 types of nodes. It actually has far more than 2 types of nodes, but we only care about 2 of them. You have the Haswell nodes. We have roughly 9,408 of those. Each of them is a dual socket Haswell. And we have 9,500 Knights Landing nodes. And while very similar, because they're both Intel with very, very similar instruction sets, and you'd think there wouldn't be a lot of tweaking, there are some advantages that each node has over the other, and we want to take advantage of that. The goal of Tabasco was to perform a hybrid run in which both stages are utilized. We put the coarse scale solver and less compute-intensive work on the Haswell nodes, where we're not necessarily going to have much multi-threading options. We just need something that runs. I mean, like, we're not going to optimize Redis, for example. And then we put the fine-grained solvers on the KNLs, where we can fine-tune and work with the multi-threading and OpenMP level parallelism. And this actually worked quite well in Charm++. We just used the logical machine entities to identify KNLs and Haswells, and then wrote custom mappers to assign chars based on physical node type. If that sounds complicated, it really wasn't. I just basically queried every single physical node and said, how many processors PEs do you have? And depending upon the number of PEs, I knew if it was a Haswell or a KNL, and then I just assigned those to simple mappers. If there's a better solution, I would love to hear it, because just writing that made me feel really dirty. But it works, and it's actually on GitHub under the ExMatEx Tabasco project. I forget what the branch is called, but it should be pretty obvious. So going back to that mapping, because we are good software engineers, we use the same mapping as we actually finally put the fine scale solvers on the KNL nodes. So for our host platform, we only use Trinitite, because currently Trinity, you can't actually use the Haswells and KNLs at the same time. That's going to happen after Open Science finishes. So we ran with 3 types of nodes for our testing. Dual socket Haswell solver nodes, so 32 MPI ranks per node. KNL solver nodes, 64 MPI ranks per node. And for the sake of just doing a very simple comparison where we have not done the fine tuning to figure out what the best ratios are yet, we had a dedicated Haswell organizer node with only 4 MPI ranks on it. So essentially, we put every single coarse scale model on that single Haswell. It obviously limits our scalability, but it drastically simplifies testing just to make sure everything works. because the goal of this is not so much the performance data, although I am going to show that, but was just to make sure this does work with the software stack we have, the techniques work, and then we can fine-tune and find better techniques as we work on also fine-tuning and making a much better implementation. So the simulation we ran, we only used the Taylor solver because we just wanted to have a very simple test, and we were partially waiting for better OpenMP support, so thanks, by the way. And we have no adaptive sampling on because, again, we want to maximize work, minimize communication. We don't want to have contention for these tests, so, and also the more work we have, the better things look. We reused the run from Open Science Phase 1. I'd say the pertinent portions are we have 4 domains which correspond to the 4 coarse scale chars, and we have 34,944 fine scale evaluations per time step and 100 time steps. Before I show the timing results, I just want to remind everyone this is very early work. It may not be indicative. We're still working on actually making it better. But just in terms of raw execution time, we actually have a surprisingly good performance gain from using the KNLs as solvers instead of Haswells. Intuitively, this kind of makes sense because it's 64 ranks per node versus 32 ranks per node, but it's still, they're slower cores. It's pretty nice. But the thing is, just performance is not what we're interested in. As was mentioned, energy is a concern. So we did very rough approximations of energy savings. On Trinity, there are lots of wonderful tools and metrics we can get access to show the actual power consumption. On Trinitite, the development cluster, there aren't. So we had to do estimations. To do this, we used TDP. Never use TDP. If you Google TDP, the first result will say, do not use this for power estimations. But we did anyway because we just wanted to have some data. So it's a very simple equation. We just used TDP times the execution time, and we assumed all else was the same, which in this case is actually somewhat fair because they are the same machine. But again, take this with a humongous grain of salt. But again, fortunately, it makes us look really good because now just doing raw power, you can see the KNLs are a big savings. And if we just do the actual ratio between them, you'll see that just out to 14 solver nodes, so that would be 14 times 32 Haswell ranks or 14 times 64 KNL ranks. I should have done that at the ahead of time, but I didn't. We have on the order of a 30% power savings over using KNLs versus Haswells, which is good because it shows a good reason to use KNLs. And with Char, it was actually quite easy to use the KNLs. It was the exact same code. The portions where it's not going to be the same code what we're working on right now, but this was just a proof of concept. Does this work? Is it worth pursuing? Or should we never mention hybrid runs again? And the end result is we're doing hybrid runs. And so that's the talk. I went way under time, but there's a break coming up, so questions?
For the power energy estimation that you did, the Haswell and KNL hardware at least have performance counters or MSRs that can actually tell you power and energy and so forth. Some systems they're accessible, some they're not. I don't know how Trinitite's configured.
Trinitite I asked, and the answer was effectively it's not worth it. But on Trinity, we should be able to get all of that data pretty easily. So when we do the real performance runs, we will have the real data.
Cool, thank you.
This is more designed to just show people and say, hey, look, we're not wasting everyone's time. This is actually worth doing.
Yeah. Okay.
I wonder, for your last slide, when you compare energy usage with KNL and Haswell, is that anyway normalized with the compute time? So this is a unit, the unit F4 that was computed, or was it normalized? You know what I mean?
I'm not 100%.
You compute a problem and you run it to completion. I assume with one, and then you do the same, and that may take longer or less long or shorter time.
I just took the power ratings, power values, because again, might be an E-leg, but I'm horrible at energy versus power terminology. But we just took raw execution time times TDP to get power, which gives us this graph. And then all I did for each of those was I divided the, KNL difference over the Haswell value. So this is, the KNL was used 30% less power than the Haswell.
Okay, so you didn't. So I would still divide it by the execution time.
Okay.
That would be a more fair comparison, because that's compared to a given task.
If I
that's
divide by
completed,
execution time, I'm just doing a TDP of 2 Haswells over 1 KNL, which will still look good, but
I don't know. I feel like that's a more fair comparison, because you're comparing the two. You're comparing the same amount of work that you want to compute with the two devices.
we can talk offline about the better way to present this. Again, I just want to point out straight up, I should probably not have this data, because again, you should not use TDP for these computations. This was just to get some back of the envelope. Is this worth looking at?
Thank you.
Oh, yes.
So for our code, we also need to look at KNL next, because that seems to be what we have to deal with in terms of supercomputers. So your experience with Charm++, basically you recompile your code and it will at least run. Is that?
Yeah, it ran with no effort at all. We put more effort into other parts of the stack than we did for just using the KNLs.
Okay, that's good to know. And then I guess in terms of other things, because of the different vector units and everything like that, I guess that's what you're looking at next in terms of performance, if I understood that statement, because you have, AVX 512 and all these things that you now have to deal with on a different architecture.
Yes, I didn't quite get into it too much, but we have the Taylor solver, which we use for this, but we actually want to use the VPSC solver, and there is work ongoing to make that more KNL ready.
Okay. All right, thank you.
So actually, if you don't mind, I'm going to ask the audience a question. Anyone here has any tips or points about Charm++ codes on KNL? I think one of the things that I think about is the PE map. If you run multiple processes, like you saw in Jim's talk yesterday, if you want to optimize performance, you have to typically use multiple processes. And if you use multiple processes, you have to carefully use PE maps so that you have the right sets of cores assigned to right sets of.
Were you using the MPI or GNI machine layers?
MPI, because the GNI stopped compiling. But that might be an us problem.
Oh, sorry.
So when you're running both on Haswells and Knight's Landing all at the same time, the speeds of the processors might be different. Mm-hmm. So we have speed-aware load balancer to indicate that. So you can use to balance the load in the case of speed difference.
Okay.
Any other questions? Oh, sorry. Yeah.
Related, did you use any of the charm load balancers? And did
not
that
for this
interact with your handwritten mapping scheme?
For this scheme, we did not, and also my handwritten mapping scheme was just round robin over whichever ranks we want, whichever PEs we decided to use.
No further questions. Let's stop here exactly on time. Thank you.